changed here is that now our jumps are smaller. See, like before, our jumps in voltage, it was 2 voltage DC, 2 VDC. Now it's just like 1 VDC or negative 1 VDC, right? So it means that the current, it's gonna move smoother. So let me actually start the current from the same point that we did before. So in this case, let's say like if you start from here, it goes here, then here, like it goes here. Maybe I'll do just like a little bit more realistic. Go here, here, it's like the voltage changes to 0, so it starts going down. Voltage changes to negative VDC, it starts going down, and changes to 0. Maybe I should do like more, yeah, to be more realistic. It's like gonna be like this. It should have been like a little bit. And it would continue like that. Okay, so here our current actually looks a little bit better, right? A little bit more sinusoidal. It still has a lot of harmonics, but looks better than bipolar modulation. Okay, the other thing that we can do here, we can see here, is that by changing the by basically having a delay between these switches, we can change the voltage level as well, the amplitude of the voltage RMS AC that we're gonna have in the output. So we can change that eventually, right? So but in the bipolar modulation, we didn't have that option because we didn't have any delay. We just like to VDC, negative VDC. There was no 0 that we can just like make this bigger or smaller, right here. But you have the option to change the amplitude or magnitude of the voltage as well. We also can change the frequency, right? By changing the frequency of signaling, we can change the frequency of the output. The same thing here. And as we increase the frequency, the harmonics are also gonna be smaller. So that's basically the difference between bipolar modulation and unipolar modulation. Okay. So again, I want to say that like here, like we didn't have like here, like we have because we only had one comparator, right? So like this is basically what we end up with. Like we don't have any 0 here, but in unipolar we have positive VDC. We also have a 0 voltage in the middle and then negative VDC. Okay. And if we wanna implement the control for the gates, how to fire them, this is how we do it. We have a comparator, we have switch 1, and complementary of that would be switch 4, and we would have another one for switch 2, and complementary of that would be switch 3, or switch 3 and 2, sorry. Just like, yeah. Okay, so this would have better quality, and you can see because the jumps are smaller, basically as if we have more like effective switching, right? So you see like the changes in the current are smaller compared to bipolar modulation. Now I mentioned comparators, so I want to like do a small review for you guys, a brief review for you guys for like this concept of comparator. and how we use that to create these PWM pulse width modulated signals that we apply to our switch gates. So eventually you want to see like what a PWM, how PWM is generated. But let me just like remind you of the concept of op amp that we saw before. Well, like in real circuits, we're not gonna have this, but this can be used to explain how PWM is created. So if you remember, if you have an op amp with positive power supply and negative power supply, let me call it VCC plus and VCC negative. Okay, if we use op amp in open loop, it has two signals, two input signals, and it takes an output signal. Okay, so if you use op amp with open loop, or if you also like have positive feedback, then op amp eventually saturates, right? Because any small changes between V1 and V2 make VO go either to plus infinity or negative infinity, and that's going to be cut out by these power supply limits, because V out is always between VCC plus and VCC negative. So here, this concept can be used to compare V1 and V2. How? If V1 is bigger than V2, V out would become VCC plus. If you can't remember why that's the case, because the output of an op amp is basically A, which is a very high gain, times VP minus Vn. So if V1 is bigger than V2, this is going to be positive. This is a very huge number. This becomes a very huge number, right? So op amp goes into the saturation mode and VO would be fixed at VCC plus. If V1 is smaller than V2, VO, it's going to be equal to VCC minus. Okay, so of course, this is not a practical circuit, and if you remember from 3130, you can improve this by using Schmitt trigger instead of just an open loop op amp. This is not part of the course, by the way, but just I wanted to remind you that we can have something like this. Yes, R1, R2. Right, this is and this is grounded. And then here you would just like basically provide V1 minus V2 using a subtractor. So here, using the Schmitt trigger, you can also do the same thing. So here output, it's gonna be VCC plus if V1 minus V2 is positive, and it's going to be VCC minus if V1 minus V2 is negative. The reason this one is better than just like regular op amp